Hello again. Tonight we're going to talk about the European Space Agency's Euclid Space Telescope. What are space telescopes? How many of them are up there already? Where they're all located? Are we launching any more of them? Or do we have duplicates, and why? That, and then we'll follow up at the end with the details about the Euclid Space Telescope. So, do we need to launch another space telescope? These are the space telescopes that are already up there. Some of them you might recognize, like Hubble Space Telescope, Gaia, James Webb Space Telescope. I took the word space telescope off the ends of them because it just makes the name so long. But they're up there for different reasons, and they're at different observing points. And there's also a long list of ones that were up there that aren't up there anymore or are not operational anymore. So I left those off the list because otherwise it would just get very long. So there's more on the way. Euclid was launched to Lagrange point 2, and we now have first light images from it. But in 2023, throughout, through the rest of the year, 1, 2, 3, 4, 5, they're going to be launching 5 more space telescopes. And then in the coming years, we've got in 2024, 2025, 2 in 2026, the big one, Nancy Grace Roman, in 2027, and then the bigger one, the Ariel, in 2029. But the one that you don't see on here, because we don't have a launch date for it yet, is the Carl Sagan Space Telescope. Think of even bigger than the James Webb Space Telescope. Don't know how they're going to fit that inside of a rocket. Maybe they're waiting for Starship-sized rockets to launch it. But that's going to be after that. So why are there so many of them up there that are apparently duplicates? They have very similar capabilities. It's because the kids aren't playing nice together. So you have the James Webb Space Telescope, which was a joint program by NASA, the European Space Agency, and the Canadian Space Agency. And Euclid is 13 countries in the EU. Yep, it's from European Union, but not all the countries contributed financially to it or technologically to it. And the ESA Euclid is not actually a NASA program. NASA is not chipping in enough to cover its cost to say it's a NASA ESA program like JWST was. But NASA did produce some of the instruments that are on board Euclid and then turn them over to the ESA for the probe. And they loaned some scientists for discussing what instruments would work well, how to simulate them prior to launch, and that kind of thing. So it reminds me of the old TV commercial, and I helped. So nations that on various programs play together are the US's NASA, the European Union's ESA, Canada's Canadian Space Agency, and Japan's JAXA. The nations that predominantly launch things independently. So when they launch a space telescope, it's all for them, not for anybody else to use. Although they might make the science available for other nations to use, other nations just don't have any say in what's going on with them. So Russia's Roscosmos, China has their CNSA, India has their ISRO, and then there are 2 of them with the same acronym. The Israeli Space Agency is ISA, and then the Italy Space Agency is also ISA. Isn't Italy part of the European Union? Well, like I said, only 13 countries in the EU are part of ESA. So if there's so many space telescopes up there, don't they run into each other? Are we running out of space or whatever? Well, some space telescopes are swappable. They actually take them up in a capsule, mount them through a window or through a portal in the International Space Station, use them for a while, and then either put them on a shelf inside the space station in case they need them again, or actually bring them back down. There are low Earth orbiting space telescopes that are short-lived. They're only for observing, particular celestial events, and after 5 to 10 years, they'll burn up unless they get boosted back up into orbit, like the Hubble has had done to it several times. There are geostationary Earth orbiting satellites. Strange as it sounds, they last about 6 or so years. Then they run out of their orbital station-keeping fixed-size tank of fuel. And before they run out, they goose them over the Pacific or to a higher elevation orbit and then shut them down, leave them parked there. And we talked about that a couple of weeks ago. Then there are orbits that are sun-synchronous polar, and they last, strangely enough, a little longer, about 7 years. And then they park those because they're actually going North Pole to South Pole or South Pole to North Pole. And they rotate at a speed that's roughly the same as the Earth rotation. So the Earth rotates under them and they observe in stripes. And then you've heard of the Lagrange points. The popular one for looking out into space is L2. The popular one for observing the sun is L1. And they last about 6 years until they run out of fuel or they run out of like liquid helium, which cools their instruments, and then they move them around. So when Gaia, for example, runs out of fuel in another 3 or 4 years, they might try and do some observing with it, but it's going to get in the way and they don't want it to be uncontrollable. So while it still has fuel, they will push it into kind of an L1 to a sun orbiting orbit. But if you want to look out into space, L2 is the popular orbit. That's where Gaia, JWST, and now Euclid are there. And JWST and Euclid have flattened, tilted, elliptical orbits around L2. They don't actually sit at L2. They orbit what they call a virtual halo orbit around L2. But Gaia is different. Gaia is a survey telescope, and it wants to move very quickly. So it's looking over the sky quickly. So it's doing what is known as a virtual Lissajous orbit. So it's kind of this corkscrew stripe that's oscillating back and forth. That consumes a lot more fuel. That's why Gaia is probably not going to last as long. And we've mentioned L1 solar orbits. They can be circular or elliptical. And, it takes more fuel to do that, so they'll last about 6 years. The Stereo A and Stereo B, those were launched into L1 advancing and retarding orbits. So Stereo A was after the sun. So it was launched around to the side of the sun that would be bringing it back closer to Earth. And then Stereo B is the behind. So it was launched so it would be behind orbiting the sun. So they continue to move and you'll lose them behind the sun and hopefully they come out the other side. Stereo A has come back, Stereo B has not. And then we have the deep space flybys, the Pioneers, the Voyagers, New Horizons. They're going to be out there. They're radioisotope thermoelectric generator powered. They'll probably last longer than their budgets. People will go, get tired of them and pull the funding and just let them go out there and not talk to them anymore. And after you let them go out there for long enough without course correction or course correction fuel, you'll lose contact with them. So I mentioned what they do at the end of life. If you're at the end of life, it's typically because you either have an instrument failure, electronics failure, or you run out of your orbital maintenance fuel, which is usually the one that does you in. But if you don't have enough fuel to stay up in your low Earth orbiting, you just fall back and burn up. If you're geostationary or geosynchronous, you'll slowly drift to the west and be out over the Pacific. But once you stabilize your orbit, you might be up there for hundreds of years. Here's a strange thing. If you're at an L2 orbit, your orbit will eventually degrade into a wide solar orbit. Because remember, they're in a halo orbit around L2. And as long as you're on the upside or the downside of that orbit, when you lose control, you'll just slot right in and go into a very elongated solar orbit. So the idea, according to the United Nations, is leave enough reserve fuel so that you can put yourself into a known stable condition or burn up. And this is when they're observing, when they're capturing information, how do they look at what they're looking at? In the case of Gaia or Euclid, these are wide field survey. So they won't just have one imaging chip. They'll have a matrix of imaging chips. It's not that they took individual pictures and lined them up. They're individual chips that are in a plane, they're in an array, and they expose all of them at once. So it takes pictures of that wide area of the sky. It's maybe a couple of degrees at most, but as it's moving, it goes stare at that space, snap. And then it stops taking the image, stores the data, sends it back to Earth for post-processing, and then it steps to the next spot, snap, takes another long duration image. So that's what is known as a stare and step, or step and stare. Then you have other telescopes like the Hubble and the James Webb, where they have multiple instruments that they can point at the target all at the same time, and the field of view is much smaller. Think about, okay, one of those imaging chips is looking about 1/4 of a degree by 1/4 of a degree, each one of those panes. But you've got JWST here, full framing on Jupiter, without wasting a lot of pixels around the side, which puts more of its resolution, more of its ability to pick out detail on the target. So it's better at shooting smaller targets. So you have wide field and you have narrow. And then not all these space telescopes operate in the same wavelength. You might have dedicated telescopes for certain ranges. Things like the Hubble try and be like one-stop shopping. So the Hubble actually has filters and separate instruments for doing UV, visible light, and near-infrared. There are dedicated telescopes for gamma, X-ray, ultraviolet, the broad bands of ultraviolet, visible, things that people can see, and then you go a step down from that into darker but still visible, going into near-infrared. And then you have the classical infrared, which is actually starting at very, very dim, dark red, and then goes into near-infrared, medium infrared, and maybe a little far infrared. And the next thing down you have from there is radio communications. So you've got micrometer, submillimeter, meter, radio wavelengths. And as we're talking about, future telescopes, if we ever put up a gravity wave telescope in space, it'll either be one telescope that is, miles long as a giant L, or it'll be an array of separate telescopes that use lasers to create a flying array of telescopes, and they'll measure the separation between all the individual telescopes. So it could be not one telescope, but maybe 24 of them as an interferometry array. And then you can see an image there of the various bandwidths. So the very long radio wavelengths all the way down to the 10 to the minus 12 meters gamma rays. Sometimes you can't mix and match. Hubble does a really good job of working from UV all the way down into near infrared. But let's say you said, I want to throw in some gamma. How would I observe gamma? Gamma is too high energy. You cannot use mirrors or lenses on gamma. You need to use thick osmium plates that don't reflect it. They absorb the energy you don't want. So there's not really focusing so much as there is clipping. So you can narrow the beam down to do your gamma image. But what you're really doing is saying, ignore all the stuff around my frame of view. And that's gamma. X-ray is like an X-ray image. You use electromagnetic coils to steer and concentrate the X-ray beam. No mirrors, no lenses. And then you get into ultraviolet through near infrared, and it's predominantly silver-plated glass mirrors. But then you dip down into the deeper infrared, mid-infrared to far infrared, and you need gold-plated metal mirrors because the particular wavelength, silvered glass doesn't really concentrate well. So you don't use lenses, you just use mirrors. And then for radio, it's depending upon the wavelength, you either have a solid or a mesh parabolic antenna, and it reflects the radio waves down to the primary and then up onto the secondary. Or you might have an array of them joining all together. But basically, you might have more than one telescope up there simply because you've got different wavelengths that you're looking at with different telescopes. So let's say we have a particular kind of space telescope that's optical. And it's going to be taking narrow field images. So it's going to take pictures. It's not going to do matrix, step and stare. So how is it that it takes pictures? Well, you need a carousel or beam splitting so you can direct the different wavelengths to different sensors. You might have photometers that only are good at measuring brightness, that they measure like how bright is that star, but they might not care about what the actual color of the star is. Or, you're not going to get a picture from one point of data, but you're going to get the amplitude, the brightness of the star. Then you've got imaging, the typical stuff, makes pictures. It can be monochromatic, so you only get gray images, or it can be genuine color where you have a bare matrix of different filters covering the imager. Or it can be false color where you take all gray images, but you have filters on the front of it to give you your red, green, blue, and luminance, and then you mix all that together. Or you could be looking for the chemistry of the things you're looking at. So you do spectroscopic analysis. It's not so much you want to take a picture as you want to measure how bright or dim, or where there's a notch or missing or added amplitude for particular wavelengths. You use a spectroscope for that. But what they found out is if you're measuring the rotation of a galaxy, the part that's rotating away will be blue shifted. The part that's rotating away will be red shifted. The part that's rotating towards us will be blue shifted. So you can use your spectroscope to identify the velocity of rotation of the galaxy. And then you have a whole bunch of different wavelengths and filters that you can use for taking various kinds of pictures. And coronagraphs, they've made some advancements, and they started making the advancements with the Swift infrared solar telescope, in that instead of having a disk that sits in the middle of your camera to block out the bright light from the star so you can get the dimmer light from exoplanets or asteroids or comets, instead of having this metal disc that just blocks out the star, what if your imaging chip had in front of it a giant array of 20,000 little shutters, like a Texas Instruments LCD projector has shutters, and you just flip open the shutters where you want to get light in, and you don't open the shutters where you want to block out the light. This allows for things other than just a circle, because if you happen to have an exoplanet orbiting a binary pair, you may have two stars you need to block out. And having only one disk that's only in the middle, how do you block out the other star? Use the shutters. Okay, so now we get on to Euclid. This is like Euclid in one page. So Euclid was produced by a consortium of 13 EU countries, plus a little side effort in instruments and scientist loaning by NASA. It's about 14 feet by 10 feet. It's it's a little elongated. The primary mirror is 4 foot round, Hubble-sized kind of mirror. The maximum field of view is just under 1 degree. To think about it, the moon is a half a degree. So the maximum amount of sky you can see in one image before it steps is about 2 moon diameters. It was launched on July 1st, and it was sent out to Lagrange Point 2, and they used a SpaceX Falcon 9 to get it there. It's in a virtual halo orbit about L2, just like James Webb Space Telescope, although the orbital parameters are a little different to keep them where they never run into each other. And if you look at this strange shape, you'll see that that flat plate, that's really where the solar panels are, and that faces the sun and keeps the sun out of the instrument. And then the telescope is actually on the top side and points 90 degrees away from the sun. But unfortunately, they have a light leak. So as long as they keep the bottom side not squarely tilted towards the sun, but rotated just slightly, they can avoid the sunlight making it up into a crack in that tube shield that shows up in the instrument. And at first, when they turned it on, they said, why is everything so bright? Stars shouldn't be that bright. And it turns out it was a light leak from the sun that was increasing the amplitude of their detections. So as the saying goes, you have to keep the hot side towards the sun and the earth and the cold side towards space, which actually limits its viewing angle over the course of the year more so than with the James Webb Space Telescope. If you talk about how accurately can it point to a spot in the sky, it can point to a spot in the sky that's 35 thousandths of an arc second of degrees. So pretty sharp pointing capability. Because of how much time it's going to take to download high resolution images, and because it has to share with other European Space Agency space programs, it only gets 4 hours a day on a particular Ka band of 27 to 40 gigahertz out of Cebreros, Spain. So why isn't it using the Deep Space Network and get some time on the NASA Deep Space Network? Because as it turns out, they couldn't get enough time on it. So they only have one satellite, one antenna that's going to be pointed at it, and only gets 4 hours a day. Now, why would it only get 4 hours a day? Because it's only one antenna. L2 is always in the same space relative to the Earth, and the Earth rotates. It only gets to look, that receiving antenna only gets to interact with Euclid for 4 hours every day, based upon the rotation of the Earth and what direction L2 is at. Although, it's not that far away. It's 1.5 million miles away. So it gets a pretty good data rate. It gets 55 megabits per second. It has 300 gigabytes of onboard storage. So it can take pictures, store them, and then when it comes back around in contact with the Earth, download it. And like I said, they're working on their first ladder calibration images. They haven't started taking science images yet. It's a wide field survey telescope, so you can see in that middle picture, it does the step and stare, and every one of those squares is another grab of image. Its instruments are a little unusual. It's touted as being a infrared telescope, but it actually has a little bit of near infrared and some orange. So you'll see that there's no ultraviolet, no violet, no cyan, no blue. And strangely enough, it can't dig way down deep into infrared. So there's no medium wave infrared, long wave infrared, or far infrared. It's all near infrared. It has two different imagers, one that's 600 megapixels. That's the big matrix. It's a 6x6 array. And it can see from mid-green to yellow to orange to red to near infrared. So we'll see it getting, let's say, some visual with no blue in it, no purples in it, which is going to look weird. So they'll probably false color that. And then for all their photometry and spectrometry, they have a different 65 megapixel camera. And it's got a whole bunch of filters on it, but it's only 2K by 2K resolution. Now, what they're looking for is dark matter influences on the shapes of galaxies. And because it can do velocity measurements for the spectrometer, it's going to measure the rotational velocity of galaxies. Its mission, like I said, is going to be about 6 years. That's when it runs out of station-keeping fuel or coolant for its imaging chips. It's going to get about 1/3 of the intergalactic sky. Now, that means, think of it this way, as it goes in orbit with the Earth around the sun, there's a range that it can shoot. It cannot tilt up too high because then the sunlight will come in, and it cannot tilt down too low because then the sunlight will come in. So it's got a swath that it can observe in up and down. So you can see the step and stare. It doesn't go all the way overhead, and it doesn't go all the way down. So that's why it's just 1/3 of the sky. They estimate that it will look at 10 billion galaxies in its lifespan, and it will produce 170 petabytes of data. And the last time they had a telescope similar to this, it was the Planck Space Telescope that ended its mission in 2013. So here is its timeline. So it's launched in July. Mid-July, it arrived at L2. It verified its fine guidance sensors. And then on the 15th of July, it started to take pictures, and that's when they found out, not quite in focus, and we're getting a lot more light than we thought. And they had to track down where they were getting light from And they found algorithmically a way to correct for that. So they started taking its first focused images. They took a field about 1/8 of a degree, so the size of a quarter of the full moon. So they're going to start doing some more testing. And when they get it all running to their satisfaction and they've adjusted the programs for the foibles that they've seen, then they'll open it up for science program measurements. They've already got a lot of science booked for it, so they may have to adjust that given that they don't have as much freedom to point as they thought they were going to. Now you can see down below this big picture that the one on the left is black and white, grayscale. The one on the right looks kind of reddish or orangish, and that's because it's using the two different cameras. So in conclusion, at first blush, you may think there's a lot of space telescopes up there, but there's reasons for it. There's international duplications because not everybody shares. There's where you have to put them to see what they want to see. So you've got putting them up on the ISS, low Earth orbit, geosynchronous orbit, sun synchronous orbits, out at L2, out at L1 or solar orbits. So you can have two different telescopes with similar instruments that are looking at different things. And then you've got the designs that are specifically for looking in specific wavelengths or looking at targets in a certain way like survey or narrow field. The kinds of observations they're going to need, which means the kinds of instruments they have. So photometric, how bright is that star? Pictures, and then chemistry. But you never know what you're going to see until you put something better up there. And just as this telescope is an improvement on the last telescope, the Planck that they had up there, improve the instruments, every 10 years or so, launch something else, and learn new things about the universe that you didn't know before. And then we have a few links. And for those people that want the nitty gritty, I actually included the links to the Teledyne imaging chips. They've got a lot of PR on the imaging chips. So rather than NASA commissioning unique chips, they bought off the shelf, which saves us money.
Yeah.
Also means they can build a space telescope faster.
Time for questions?
Absolutely, anytime.
If I heard correctly, all of the information you've given us is justifying why there are more satellites out there and that they're all doing good job, or they're duplicated for a good reason. They're all out there because they have a telescope that's a different size that has to look at something different. Is there any junk or any is there any bad stuff going out there? Is there any fraud going where you pay more money to get one up there? And, I don't know.
The ones that are in low Earth orbit, they obviously fall back and burn up within about 5 years. The ones that are out at L2, L2 is a precious real estate. So as the telescope that might be out there like a Gaia starts to run low on fuel, they use the remaining fuel to scoot it out of the L2 halo orbit and put it in a very large sun orbiting. So it's actually in the same orbit as the Earth, but about 1.5 million, actually 2 million miles farther out. So it's orbiting the sun, and it takes longer than a year for it to orbit the sun, but it's out of the way. So if you think about the orbit of the Earth, and then you go about another 1 million miles out, there's a lot of room out there for us to put junk. Far more than the entire orbital sphere of the Earth. But the UN, I don't think it was quite 10 years ago, basically put out a mandate, not that, any country has to follow it, but countries that understand what's going on will follow it. And that is, don't put something up there unless you include a plan for when it's no longer functioning or when it runs out of fuel and what are you doing with it. So there's a lot of stuff up there. The only redundancy that I see is when nations don't play nice together and they put up two space telescopes for the same reason, or they both want to put landers at the south pole of the moon looking for exactly the same thing because one of them is India and the other one is Russia.
So there's nothing about money here. nobody's being greedy and trying to send more satellites up than we need
Um,
to make money.
I'd say that there's a factor of that for the corporations that are helping to build the satellites. But I think NASA's gotten clever enough to say, if instead of commissioning a company to build custom chips or custom sensors just for us, is there anything we can reuse off the shelf?
Ooh.
So the color camera that Juno has is literally an off-the-shelf 2-megapixel color imaging camera. The 2 imaging cameras that Euclid has are Teledyne. There's slight variation due to the filters, but the chip array itself is just a matrixed up version of something they had off the shelf. So that reduces your tax dollars cost of putting these things up there. But I'd say, the Boeings and the Rockwells and the Airbuses and things like that, they're still making their money off of it.
But they're not greedy. I'm very happy to hear this. Something in the news that doesn't have greed or control or power.
I will not say that they aren't incentivized to up the bill. I will say they're doing what we ask of them, and if we stop asking, they'd have no revenue coming in. But I don't think that we're creating newer and better instruments just because we want to make sure they have money. I think we're actually doing it. Like the difference between the Planck instrument and the Euclid instrument is it's a generational improvement in the electronics, even though the basic design of the telescope looks very similar. But
I'm happy to hear it. Thank you.
But yeah, I'd say rather than them building one-shot dedicated stuff, they're trying to save money where practical. Think about it this way. Euclid was launched with a reusable Falcon 9 first stage rocket. And the fairing halves that were covering it, those were also reusable. But back when the Planck telescope was launched, that was a one-shot booster. The total cost of the programs may not have come down much, but they certainly haven't kept pace with inflation, and everything's a throwaway. I will say that Artemis, except for the capsule that the astronauts are in, everything below it's still a throwaway. But Starship is not meant to be a throwaway.
Okay, thank you.
Amazing.
Yeah, I probably know more than I should. But if you want to see a guy that really knows all there is to know about such things, it's watch Scott Manley's channel on YouTube.
Heard of him.
He's very good at all the minutia of the various rocket programs and space, probe programs and such. But if you want to watch the actual details of how all those rocket engines actually function on the inside, watch the YouTube channel, some of his earlier videos called Everyday Astronaut. He's just an everyday kind of guy that got the itch and dug deep into it and learned a lot of minutia about how rocket engines work and how the fuel flows work and how do you get it spun up to that high speed and how does it not melt itself and all those various things. But he not only studied U.S. rockets, he also studied the rockets from Russia and the USSR. So you can compare and contrast how does theirs work versus how do ours work, kind of thing.
Cool.
The rabbit holes just go on and deep, and
Are we turning off recording now?
We can if there's something you'd like to say off the hook, so to speak. And now we'll stop recording.